Welcome to the Webster CyberLab. We're going to talk today about the use of the CyberLab for doing science of cybersecurity. And this is an outline of our talk. So the science of cybersecurity, as all science, is based on the notions of causality, testability, refutation, and adaptation. Cause works via mechanisms to produce effects. And when we see here, C, arrow M, cause, mechanism, and effect, that's foundational to all science, and it's an assumption of science. A scientific theory then has to be testable, and it has to be testable by an experiment. And the idea is that the experiment can show that the theory is wrong. If you can't have an experiment that shows you're wrong, then it's not science. And there's another thing to note, and that is for a universal theory, for a theory that applies to everything or to an infinite set of things, you can never prove it's right. All you can ever do is test it again and again. So you test and measure something or another, and the measurement has to be compared to what the theory predicts for the measurement. And if the measurement disagrees with the theory, either your measurement's no good or the theory's wrong. When a theory is refuted, that is, the measurement's right and the theory's wrong, then we have to adapt the theory or try something else. And I'll give you an example of a scientific theory. That theory is that the Earth is flat. That is, in fact, a scientific theory because it meets these requirements. And there was an experiment that was done long ago that proved that it was wrong, called circumnavigation. The globe was circumnavigated. So science developed a new theory, and that's how science works. So I want to talk about a theory of denial of services, because that's what we're going to be talking about today. The theory is that resource exhaustion in a computer is what causes denial of services. So the cause is using a lot of resources. Specifically, the performance scales. The amount of performance available goes down essentially linearly with the amount of use until you reach exhaustion of the available resources. And then whenever a critical resource is exhausted, that is the one that runs out that you needed, then you have a knee point, as you can see here, the critical threshold, and you get denial of services. So that's the theory. And there are examples of these critical resources: CPU time, computer time, file handles, disk space, and so forth. There are a lot of different resources used in computers, and by using up any of them, you can cause things to slow down or stop. So the problem we have is, how do we test that theory? Well, testing the theory involves isolating a specific resource. In particular, we want to have one of those resources tested at a time, so it's independent of the rest of them. You limit that resource to a finite known value, and you measure performance as you change the consumption rate. So you consume more and more and measure the performance. Presumably, if the theory is right, it'll go down and down until you use them up and there's none left. And when you run out, at that threshold, you should hit the knee point, and all of a sudden services should be denied. That's what we do to measure it. And then, of course, we can increase the available resources and test over the range of different resources to show that threshold is driven by the resource quantity. And that's how we demonstrate that theory. In particular, as more resources should allow the services to go linear longer. Now, what might happen, of course, is we might double the resources, but not double the knee point. And that means there's some confounding factor, a nonlinearity. And the theory says it might be that we ran into some other resource limitation. So we have to figure that out. Now I'm going to show you the experiment. This is a demonstration of the CyberLab with a distributed denial of service attack. In this particular case, we have a server D14, a client that communicates to the server, and two attackers. We're logged into the client here, and this is a menu to drive the attack. This is a display that tells you how much time it takes to retrieve a web page. Each one of these lines is one web page retrieval. You can see it's taking about 1/100th of a second, give or take. And the load is largely due to that. In fact, you can see up here the web server connections. That's because of the load of doing these retrievals. We're going to start attacking the server by sending requests to it. In this particular case, it's a SYN flood, and we'll tell you about that later if you're interested. So we're starting the attack, and so it's sending those floods. And you can see it's not a very significant effect on the server. And we're going to start a second attacker. That's number 2. So that one's starting, and you can see it's slowing down a little bit more. In fact, oops, looks like it's pretty much dead in the water. It will eventually probably come back. We don't know. What I'm going to do here is I'm going to turn on a defense, which is to enable SYN cookies is the name of this particular defense. And if it can get that command through, then you can see that's a long time for that particular request. But now that the SYN cookies are on, even with the 2 attackers still running, you can see that denial of service has been mitigated. And we'll just look and see what's going on. 2 attackers and the SYN cookies are defeating the attack. And I'll just go turn the SYN cookies back off, and let's just see what happens. You see it just slows down and it's dead in the water. Of course, you can see the graph of what's going on here as well. So I'm going to stop the attack on 7, and it should speed back up at some point, even with SYN cookies disabled. There it is. That was that last request. And you see it's operating, but it's still going to have some minor outages because we're not sort of fully recovered and may not be for a while. Let's just check on the status. 850 connections, so it's easing off. And then I'm going to stop the other one here. I think, let's see, attacker 2 is what's still attacking. So I'm going to shut that down. And should take a second here, but then go back to normal operations, and we'll just see the global status. Connections are back down, and in fact, in this particular case, the loop that's fetching them stopped, but we'll just restart it. So that's the basic distributed denial of service demonstration. I'm now going to do a virus demonstration. This is a virus that denies services in a different way. Instead of running these attackers against it, we're just going to, on the server, run multiple processes. So we're going to start by running just 10 of these processes. That is, we're limiting the number of attack processes that can happen to 10. And you can see the little bit of slowdown as it started. The resources were temporarily unavailable because it was being limited, but the effect was sort of negligible. And we'll just look at the status of this. There's 1 process running, and there's a lot available. And we'll just kick this up to, say, 20. So instead of limiting the processes to 10, we'll limit them to 20. And you can see a slowdown as it starts. The colons and dots reflect the processes that do run to try and deny services. But most of them were stopped, again, by this limitation. We're going to limit the processes a little bit higher this time. We're going to make it, say, 120 and see what the effect is. All those dots and colons represent processes that are executing. And you can see that these retrieval times are going up as the bar graphs go up. You can also see the load over here is much higher on the server. But it's still sustaining it pretty well, right? It's not dying. It'll take a little bit of time because it's slowed a lot of things down on the server that would normally be working. In fact, we'll have to restart the graph here because it was unable to get the information once and failed. And so you can see it's pretty effectively slowing things down. I'm just going to stop that. And we'll go get a status again and see how many processes are running up there right now. 49 are still up there. And now we're just going to run without limit. So we're just going to say, don't limit the number of processes that you can run for the attack. And you can see we're getting all these dots and colons indicating the creation of the processors. That the web server is waiting to do its first fetch, and it's unable to get that first fetch. It might eventually get one fetch out of it, but seems unlikely. So that's a crash at that point. I'm going to restart the menu and see if I can even get a global status on it. Chances are I can't. There's not enough, left on the server to even find out what the situation is. And so now these are both, of course, things we're just going to stop the server entirely. We're going to force it to shut down. There's no way you can get it to nicely shut down because it doesn't have enough processes left to even shut itself down. So this is effectively like a power off. Now, the reason you can do this safely in the CyberLab, well, one thing is either of these attacks would be wreaking havoc on the actual internet. They would be, sending lots of datagrams, or if there was somebody actually using the server, it would disrupt the server. We've just restarted the server. Also, because of the methodology of these experiments, in order to make it repeatable, everything is running here from CD-ROMs in a virtualized environment. So it's under very explicit controls, so we can get a very repeatable experiment. I'm just going to stop everything, start again. And the server is not quite up yet, so as it comes up, it will hopefully regain its capacity to run. There it is, and it's rebooted, and we're off to the races, and we can just show you the global status again and rerun the experiment, and we'll have the same results every time we do this. Well, we need to interpret this experiment. In particular, what we measured was the time till correct response. And the control variables, the things that we varied, were the available resource and the rate of consumption. And the experimental outcomes, well, normal operation as we limited resources was just fine. Nothing went wrong. We tried, one computer to try and consume the resources, but it only used up so much resource, so it didn't slow down all that much. We added a second computer, and it was able to cause the resources to become completely consumed. Then we added more resources, and we found when we added more resources that the two computers couldn't crash it, and it would take more. We don't know how much more because we didn't do that experiment here. There's another thing to note, and that is we have to subtract out the experimental overhead. And we did that, and what you can see, of course, is that the experimental overhead was one of the causes of things slowing down, and if you don't subtract it, then you'll get a false sense of the actual values for these parameters. And then as a defense, how effective is it to increase the resource? Well, it looks like it's very effective. If we just keep putting in more resources, then we'll be able to sustain more and more attack up until we get to some other critical resource. Now, the lab assignment for all of you in the audience or all the students in the course is to do a better job of measurement and testing. In particular, we want you to determine the parameters, that is, what the linear rates of change are and where the need points are for various resources. And we want you to identify and measure the confounding factors. That is, find out where it is that when one resource runs out, it gets confounded with some other resources. And find out, whether the combinations are resource independent or somehow interrelated. And finally, we want you to create a predictive equation. That is, give us an equation that we can calculate based on the settings that we have for the resources, how much resource it's going to take by the attacker in order to deny services. And we want you to do that in an experiment that you've never tried before. So we want your prediction, and then we want you to run an experiment to test that prediction. And it will either confirm or refute the validity of your equations, and then we want you to report the results. So that's the science. And I just want to talk briefly about the CyberLab. The CyberLab's for science, but science requires we isolate the phenomena under study. And what that means is we're trying to minimize confounding factors, make things very repeatable within the defined bounds of what we're trying to test, and be able to consistently measure regardless of who's doing the measurement. So anybody should be able to come in and repeat these experiments and get basically the same results within the accuracy and precision of the experimental environment. This simplification lets us examine these theories and develop these equations. Engineering, on the other hand, is more complicated, and the reason is it applies scientific results in a much more complex world. It tries to find design rules and calculation methods that work in the real world based on the scientific result. So what we need is science to do the engineering, but we also need engineering for the real world. And right now, we're building the science, and soon we're helping to build out the engineering as well. So getting back to engineering versus denial of services, if the theory is reasonably good, we can increase the right resources or achieve a balance of the resources so that we don't increase one that, where the threshold is not going to be reached till something else breaks, and then change the threshold point for denial of service by doing that. Then another thing we can do is reduce the resource usage by the machine that we're trying to defend. So it just uses less resources so it can sustain more attempted attacks. That's changing the slope of the line to push out the threshold. And finally, we can identify and predict the breaking points, and that can be used for engineering to a specification. So we can't just engineer a computer that will never run out of resources. They're finite, so they have limits. What we could do, of course, is engineer to specific limits. Here's how much we want you to be able to sustain before you fail, and in what way you fail. And then, of course, we can test these approaches in the CyberLab in controlled experiments for different combinations and measure the effectiveness over the engineered range. And if the theory is any good, the results will meet the predictions. But if not, we need to refine the theory and retry. So just finally, it's time to take questions and discussions, and I welcome any questions or discussions you may have.